Thank you so much for being here with us today. So I was hoping that just to kick things off, you could give us a little bit of an overview of what the Research Center really does, what you guys are all about.
Yes, so my institution is the German Aerospace Center, and especially the energy sector has been active in electrolysis research for almost 40 years now. So we started in last century actually with a large project. We were the first one to demonstrate alkaline electrolysis coupled to photovoltaics. It was a large project called High Solar was the name. It was a cooperation between Germany and Saudi Arabia at that time. And since then, we are working on electrolysis, but we have now a wide variety of different technologies. So we are one of the research centers that not only does research on alkaline technology, the most mature one, but also the newer ones like polymer electrolysis or steam high temperature electrolysis. And this is the one that we are presenting this year in our booth.
Okay, fantastic. So for those of us who are not quite as familiar as Professor Friedrich with all these electrolyzer technologies, could you maybe give me a brief overview of the sort of fundamental differences between them and as well where you might prefer to use one technology over the other?
Yes, so the alkaline technology is from the design, it's the simplest one, which is very robust, very mature, and you don't have to you don't consider durability issues. The polymer electrolysis is more, say, has a higher power density, so it's more compact, but you may still work on durability issues, so it's not yet proven for such long operation times as the alkaline one. And the steam electrolysis is high temperature electrolysis, which operates about 800 degrees C. It's a less mature, but has the highest efficiency if you provide heat. So you can get even efficiencies up to the level of 100% electrical conversion to hydrogen if you provide high temperature heat. And therefore, it's very attractive to research on that.
Right, of course. So when you talk about durability and possibly some durability issues, what sort of time frame are we kind of talking about? I mean, I know from an investment perspective, you want your technology to last for as long as possible, but what would be reasonable to expect out of the PEMS?
Well, what we are aiming for is to reach durabilities as well known for the alkaline technology. And there have been systems for running for 80,000 hours. So 80,000 hours is really our goal also to reach for the newer technologies.
And do you think that that's a reasonable aim?
Yes, but of course the challenge there is to demonstrate the durability, because you can imagine that testing 80,000 hours is not really easily done, because you need to test for years, and therefore we are also developing accelerated stress test to accelerate the development of components.
Okay, so I think I understand the need for condensing the 80,000 hours thing, but how does one go about developing stress tests that can meet reasonable demands and have a good facsimile for the conditions that they would be exposed to in actual use without waiting 80,000 hours to find out if your electrolyzer is as effective?
So what you do is you go to very extreme conditions and then you test the degradation mechanisms that you find. So you go to extreme conditions for, say, polymer electrolysis or solid oxide electrolysis, and then you would have to check if the degradation mechanisms are the similar ones that you find for the more normal operation over long periods of time. And this is actually also not so easy to demonstrate.
Right. Okay, so I think that's sort of where we were in our technology. Could you tell us a little bit about where you're hoping to bring this? Because you're a research institute, not a traditional consumer business. So you guys are the ones that are pushing new things and trying to do that cutting edge research. Could you tell me a little bit about that?
Yes, so what we are presenting in our booth over there is a small demonstration of how to introduce high temperature heat into a solid oxide steam electrolysis setup. As I said, this would promise very high efficiencies, but of course the electricity should be renewable, but also the heat should be renewable. In order to demonstrate a completely renewable basis, we used concentrated solar radiation to provide the heat for steam generation. And actually it's a challenge then to operate a high temperature electrolysis setup with the solar heat, because it may also fluctuate. So we have demonstrated for the first time the operation of such a solar coupled of solar heat with high temperature steam electrolysis, and this is demonstrated in our booth in the small model.
Okay, so they're at booth D62 if you want to check that out. So you mentioned the fluctuation of the solar energy is what can cause a little bit of an issue with consistent generation. Is there a way around that? Is there a way to continue using this high temperature type things with the renewable sources, which typically don't have such a consistent stream all the time?
Well, so this technology is especially interesting for also industrial applications where you have high temperature heat. One example would be steam manufacturers who are interested to replace, for example, their coke, which is used as a reducing agent, and the only known reducing agent that can replace coke would be hydrogen. So they have a lot of high temperature heat available in their industrial environment, and there, of course, this is a very attractive technology because you can provide the heat from the industrial process, and then the high temperature electrolysis will have a very high efficiency, electrical efficiency.
Fantastic. So, of course, high efficiency is super important for people that are trying to get into this. Could you talk a little bit about, if you know about like cost benefit analysis a little bit on using these newer technologies? So for an industrial capability, presumably you're wanting quite a large scale investment. Is it sound? Is it still in sort of the development phase, or could somebody already be using it today?
Oh yes, this can be used today. However, the challenges are, of course, the cost reduction. So the manufacturing processes right now are still not adequate for really high volume manufacturing. So the high volume manufacturing is essential for lowering the cost. So this is kind of the challenge we are in right now. Yeah.
And is that challenge based on not enough orders, or is it a physical issue, or the manufacturing process quite labor intensive? What needs to be done to start dropping those costs and making it a more available technology?
Well, this is, of course, goes a little bit into politics also, that right now, of course, if you compete with fossil energies, it's all these renewable-based technologies are not cost competitive. So you need either regulations or you need very cheap renewable energy in order to get into the regime that it's a business case. This may happen in some areas of the world where renewable energies are already in the range of 2 cents per kilowatt hour. And if you reach this level, of course, you can make a very easy calculation, and then you are on the same level as, for example, natural gas would cost nowadays. So then you have a business case for electrolysis to compete with natural gas steam reforming. And so, yeah, I would say the time is going in favor of these technologies. However, in the present frame, they are still more expensive than fossil-based technologies.
Right.
But we hope that there will be also the stricter regulations in the future that will make it a business case.
Okay, so regulations in favor of the renewable energies, as well as decreased manufacturing costs from greater volume orders, would help bring this technology down to a more reasonable cost for the consumer.
Yeah.
Okay, great. So I actually already went over to booth D62 and checked out your, what would you call it, your solar integrated high temperature ceramic cell. And I noticed as well that it seemed like some of it you could do the electrolysis, but you could also reverse it and go the other way. Did I interpret that
Yes,
correctly?
so this is another very attractive option of the high temperature ceramic technology, is that they're completely reversible. So you can use this same cell design for electrolysis or for fuel cell operation. And then, of course, it's attractive to go to energy storage application so that you can use, for example, you can produce hydrogen if you need it and then repower it when the grid needs power. Yeah.
Okay, so this sounds like a fairly flexible solution. So we've seen or we've heard of a lot of positives. Could you talk about some of the challenges, either with the technology or with what you're doing with the researching of it? What are some of the hiccups that you've kind of run into with that?
Yeah. So one challenge is already what we discussed, is the production technology. So ceramic manufacturing is always more complicated than other materials. So the manufacturing, large volume manufacturing is an issue. Also to go to large areas that we, of course, want to. And the other thing is the durability, of course. Even though degradation rates are very small, or very low, however, if you want to reach 80,000 hours, we still need to work on the degradation issues.
Okay, and what sort of implementation could be done or techniques could be implemented to improve that degradation? Is there any ideas behind that, or at this point it's that's too in the future to try to start improving that?
Well, some ideas are to derive system control strategies to avoid very deteriorating operation regimes. For example, there are some voltage ranges for the high temperature electrolysis where the degradation rates are higher. And from the system point of view, from the system control, you can avoid this potential range. And this is one thing that you can do. Another thing is, of course, that if you imagine high temperatures around 800 degrees, there's a lot of interdiffusion of materials, and this leads to degradation. And by introducing some diffusion barriers, you can actually limit this diffusion. Can you imagine if you go to high temperatures, materials will move more, and then it will also interdiffuse in between them. And this is, of course, you don't want that. Yeah. Yeah.
You don't want them just peeling apart? No.
No, it's just that if you have, for example, if iron from the steel, for example, diffuses into the ceramic layers, then you will get a lower performance.
Right,
and
okay.
you have to avoid that, for example.
Right, of course. So I'm not totally familiar with the manufacturing, but you mentioned that it's inherently more difficult to manufacture ceramic than other materials. Do you have any idea why that is, or is it just a material property?
Yeah, it's a material property, but it's related to statistics also. Now we are coming into a scientific issue, which may be difficult to understand for some of you, but ceramics follow a different statistics than polymer or metallic materials, meaning that if you increase the area, the cell area, if you double the cell area, you will increase the probability that you have a defect in this area by a factor of 4. Whereas if you increase the area for a polymeric material, you will have a linear increase of the probability to get a defect. Meaning the larger the area is, the more danger or the more probability of having a defect.
Okay, so this makes sense. So it's both a
it's
material
a
quality control issue
control
as well as, so then you end up with a higher cost associated with this manufacturing since you're more likely to have the flaws in material in the first place. Okay, that makes sense. Thank you.
Yeah.
So we've talked a lot about the technology that you guys are doing. Could you wrap it up with either what projects you're most excited to be working on, and as well where you're hoping to go in the future?
Well, so we are excited. I'm excited about all electrochemical technologies, and I think that actually low and high temperature technology will find different markets. So as I said, the high temperature electrolysis will find more markets in the industrial environment. I think the low temperature electrolysis will be ideally suited for dynamic operation, for fluctuating electricity inputs. So I think that both technologies have a bright future and will coexist in the market. So essentially, I think both projects or all the projects are very exciting. Yeah.
Okay, so
And we are
despite
exciting times that I think that we will get now into the area where this, as I said, the business cases will evolve and we will see deployment of these technologies.
Great. So despite the advantages and disadvantages of each technology, you feel like there's still a use case and a marketplace for these ones. So they're not necessarily a competing technology, but rather a complementary.
Complementary, exactly.
Wonderful. Thank you so much. At this point, we do have a couple minutes left if we have any questions from the audience. Feel free just to put your hand up and I will come down to you. And if there is none at this point, I would... Oh, okay, we have one. I'll come down to you.
Hello, my name is Rolf Brendel from ISFH. My question is, you didn't give an answer on how expensive the electrolysis actually is today, and I'm especially interested in small-scale systems. So could you give us a hint what the investment for a 50 kilowatt robust electrolysis system today roughly is, and how long it will last?
50 kilowatts? Yes, so essentially we'll see still, regarding also the maturity of the technology, is spread in the prices you pay nowadays. But this doesn't mean that how the prices will evolve under mass production. So right now you can account for alkaline electrolysis something like 1,000 euros per kilowatt would be a number. Polymer electrolyte fuel cells is more like 1,500 euros per kilowatt, and high temperature fuel cells still much more expensive. But this will not be the prices you will see later on.
That's good. And the lifetime of the first one you mentioned?
So the alkaline electrolysis, as I said, is very durable. So it's demonstrated 80,000 hours in many applications. And the polymer electrolyte fuel cells, also in our lab or in our testing, has shown almost no degradation for 15,000 hours operation time. So we think that also you will get into the range of at least 30,000 hours. But this is difficult to predict, of course, from the testing time we have. And the high temperature electrolysis, of course, they have still more degradation issues, but also you can expect something like 10,000 hours at least nowadays.
All right, thank you so much for that question and as well for your very informative answer. So if we have no more questions at this point, I'm sure you can feel free to visit Professor Friedrich at his booth. Like I said, it's booth D62, and I would definitely recommend dropping by to check out the demonstration. So thank you so much for your time and your presentation, and I hope you continue to enjoy your time here at the fair.
Yeah, thank you.